Welcome back to ECE 442-542. I'm labeling this particular presentation sampling frequency, Nyquist frequency, and aliasing, where sometimes the Nyquist frequency is referred to as the folding frequency, but I want to establish the connection between these three different terms or these three different concepts. And before we get too far into this, let's go ahead and establish the notation that we will be using. Omega sub s, which is the sampling frequency in radians per second, is equal to 2 pi f sub s, where here f sub s is the sampling frequency in cycles per second, or in hertz, and that's equal to 2 pi over capital T, where capital T is our sample period that we've been using throughout this semester. Another frequency that we will be talking about today is omega sub n, where n here stands for Nyquist. That also in some cases will be referred to as the folding frequency, and omega sub n we will show is actually 1/2 of the sampling frequency, or it's omega sub s over 2. And what you want to end up with by the end of the presentation here is that aliasing can occur if we have an analog signal or a continuous time waveform that has a frequency omega that exceeds the Nyquist frequency, or it's larger than omega sub s over 2. And by that aliasing, I mean that that particular frequency, when sampled at a sampling frequency of omega sub s, will actually appear as if it's a frequency between 0 hertz or DC and the Nyquist frequency, or omega sub s over 2. So even if you have a frequency of a much higher value than the Nyquist frequency, you're not going to see it that way after sampling at the sampling frequency. It's going to appear as if it's a frequency between 0 or DC and the Nyquist frequency. To make those connections, let's go ahead and look at the continuous time, or the analog case, and remind ourselves of what we should already be comfortable with, which is the frequency response in the S-plane. Let's say that we have a system described by a transfer function capital H of S with an input R of S and an output Y of S. We all should be comfortable with the fact that the output of that system in the frequency domain, capital Y of S, is equal to the product of the transfer function of the system H of S and the Laplace transform of the input, capital R of S. Now, if we're dealing with inputs that are sinusoidal, or just to give an example, suppose little r of t has an amplitude of A, and it's a cosine waveform with a frequency of omega sub 0 in radians per second. So we now have r of t described by A cosine omega 0 t. If we apply that to this linear time invariant system that now is modeled or represented as a transfer function capital H of S, then we can find the sinusoidal steady state output, or what we know is if we're shaking that system at a frequency omega naught, then the output of that system, once it's shaken or is shaken at a frequency of omega naught, will be another sinusoid at the same frequency, just with its amplitude modified and its angle or phase modified or shifted in time as what that angle represents. And what we want to get comfortable with is this magnitude and angle. That's really just the system H of S evaluated at the frequency of oscillation, or the frequency of excitation, omega naught. And the magnitude of that is simply the magnitude of this complex number, h of j omega, when we evaluate h of j omega at a particular frequency, omega naught. Meaning, if we now have the transfer function h of s, then we can find the frequency response of that system at all frequencies omega by replacing s everywhere. If our system is stable, we can replace s in our transfer function with this complex value j omega, where now j is the square root of -1 and omega is our frequency. And the frequency then we can vary between DC 0 and any value we want. And again, as long as we have a stable transfer function or all the poles of h of s in the left half plane, we can make this substitution for s, replace every s with j omega, find this complex number, which will now be h of j omega naught. If we find the magnitude and the angle, or rewrite that complex number in polar form, we now can use that information, the magnitude and the angle, to show how the original sinusoid or cosine waveform that we excited the system with modifies or gets modified by the system to produce the output in the sinusoidal steady state. It will be shaking or moving at the same frequency. Its amplitude will be adjusted by the magnitude of the system at that frequency, or the magnitude of h of j omega naught, and it will be shifted in time by the angle of that system's frequency response at that particular frequency omega naught. If you're used to thinking about the frequency response relative to the complex S-plane, let's assume now, just for illustration purposes, that our system h of s has 3 poles indicated by x's here in this S-plane diagram, and 1 0 indicated by the circle or the open circle. Then if we were interested in how that system is going to behave due to a sinusoid at omega naught, we would find that frequency in the complex S-plane, which now it has no real part. It's just a oscillating frequency. So we're working on the imaginary axis. We now go up the imaginary axis until we reach the omega naught value, or the frequency of interest, and we find the contribution of each of those poles and zeros at that frequency and find the frequency response, meaning we could graphically determine what this system's frequency response will be at each and every omega naught, at each frequency on the imaginary axis. We can measure the distance from the poles to that frequency. In this case, if we looked at the real pole on the left half plane, then we would see that it's a distance of L1 from omega naught, j omega naught, and that's just the hypotenuse of this right triangle. If we look at the pole in the second quadrant, or in the upper half of this particular picture, it has a distance L sub 2. It also has an angle of theta p sub 2 from that pole location to the frequency in question, j omega naught, whereas the real pole had an angle of theta p1 relative to this horizontal real axis. We have to look up an angle theta p1, and we would have to walk or move a distance L1. We would probably have a gain value or a constant value in that transfer function's pole zero diagram, or pole zero representation of the transfer function. That would be the k, but everything else we could measure graphically from this diagram and then compute how the magnitude is influenced by these distances, k Lz over L1, L2, L3, and the angle is just the algebraic sum of the angles contributed by the zeros. In this case, we had 1 0, theta sub z, and we subtract all of the poles in the denominator, all the angles in the denominator, which correspond to poles, which gives us our minus quantity, theta p1 plus theta p2 plus theta p3. That's now what we do for continuous time signals, we can find the frequency response by evaluating this system's transfer function on the j omega axis. And if we're interested in a particular frequency, in this case omega naught, then we would find graphically, or we could find that point graphically. We could do it analytically, but we can now find the frequency response of that system for the continuous time case, which is really just evaluating that transfer function h of s at any point omega along the imaginary axis. And if we wanted to find a specific value of the frequency response at a given frequency, omega naught, then we would plug in a particular omega naught value. What we want to do is understand how that translates into discrete time signals, or in the digital domain, what are we going to see relative to a frequency response. And we know the relationship between S domain, or the frequency domain for continuous time systems, and the frequency domain for discrete time systems, which is the z-plane. And these are related by this transformation. Z is equal to e to the st. And what we want to do is see what happens if we now are restricting our attention to the frequency response for the analog case, or we're now on the imaginary axis. What does that do relative to points in the z-plane? And we can now look at that. If we replace s with j omega, then we see that we now are looking at e to the j omega t, and there one could look at the magnitude of that expression and see that the magnitude of that, I hope, is now because of the Euler formula. This is now the cosine of omega t plus j sine omega t, and I hope you can see that the magnitude of that is cosine squared plus sine squared, which is 1, and the angle is just the inverse tangent of sine omega t over cosine omega t, which is the inverse tangent of theta. So that's just really going to be some magnitude 1 at an angle of ej theta, where theta is now the angle that has the tangent of sine omega t over cosine omega t, which really means that we are now mapping each point on the j omega axis into points on the unit circle when we replace s with this value j omega. Or for identifying a few points, if we look at j0 or dc, now if we replace omega with 0, I hope that you see that we now have e to the j0, or that's now just 1. So here is now with omega equal to 0, or dc now corresponds to 1. And as we walk up the imaginary axis, we will start to see that we now have the same distance away from the origin in the z-plane for each point, but its angle now is being changed by this relationship between sine omega t and cosine omega t. Now, in order to see how that moves, or what really happens when we keep going up and up on that imaginary axis in the s-plane, where does that take us on the z-plane? And to see that, let's now remember how the sample period capital T is defined. We have this sampling frequency, omega sub s, is 2 pi f sub s, which is 2 pi over t. We can now solve that in terms of the sampling frequency omega sub s for the sample period capital T. Or we can now say that capital T is equal to 2 pi over omega sub s. And if we make that connection, now we can see that z is equal to e to the j omega, again substituting j omega in for s, and now instead of t, we replace t with 2 pi over 2 pi over omega sub s, or we now have e to the j 2 pi omega over omega sub s. And for different values of omega, here in the s-plane, we can now pick those omegas and see where they put us in the z-plane. Let's make one observation, or an observation for a specific location in the z-plane. For example, when the frequency omega is in fact half the sampling frequency, or omega sub s over 2, then what results for z? Now z is equal to e to the j 2 pi, but we said let's replace omega with omega sub s over 2. And I think you can see that the omega sub s cancel, the 2's cancel, and we're left now with this being equal to e to the j pi. But e to the j pi, again, has a magnitude of 1, and it has an angle of pi, or in degrees, it has an angle of 180 degrees, or that's now just minus 1 in terms of where we are at in the z-plane. So now z is equal to minus 1. When we walk up the imaginary axis far enough to reach the point omega sub s over 2. Once we reach omega sub s over 2, now we have walked far enough to where we are right here in the complex z-plane. Now we're at the point minus 1. So this now represents an omega value equal to omega sub s over 2, which means that we really can't go any further. Once we have reached minus 1, once we start going around in the bottom half of the unit circle, because we're dealing with real coefficients, we really are not seeing any new frequency content in the discrete time setting. So now let's see what that means relative to what we've just demonstrated. We've just shown that the highest frequency that we are really going to be able to see or resolve in the complex plane or in the digital setting is a frequency omega sub s over 2 when we're sampling at omega sub s. Let's now look at the question, or address the question, what happens if an analog signal with a frequency beyond or above the Nyquist frequency, which is 1/2 the sampling frequency, is sampled at omega sub s. Or now we're looking for what's going to really happen, and what we will find, let me just go ahead and answer that. The answer is that frequencies above this Nyquist frequency, or above omega sub s over 2, are aliased and appear as frequencies between 0 or DC and omega sub s over 2. And before we go too much further in trying to justify this answer, let's just remind ourselves that for this class, we're dealing with real coefficients in all of our systems. And because of that, if we have a quantity j omega sub s, then we actually have to have its conjugate appearing. So complex numbers appear in complex conjugate pairs. So for every j omega sub s, we actually have its complex conjugate, which is given by minus j omega sub s. Keeping that in mind, let's now look at what we are going to obtain if we look at sampling a frequency or a sinusoid that has a frequency higher than omega sub s over 2. Let's say here is omega sub s over 2, and here's minus j omega sub s over 2. We will see that this we will now call our primary strip of frequencies in the S-plane. This is now our S-plane. Here's our primary strip. And really everything is going to look like it lives in that primary strip. But suppose that we're walking up this imaginary axis in the S-plane, and we now say, what happens if we actually sample at this particular location? Or what happens if we now had a pole even? Let's say that we had a pole at this location. And that location, let's just assume that it splits equally the distance between omega sub s over 2 and omega sub s. So let's say that we have this pole, or we're sampling at s equal to j 3/4 omega sub s. We want to know, what does that pole look like to us now, or where does that frequency sort of appear to be when we're sampling at a frequency of omega sub s. We have this relationship s equal to j, and now we are saying, oh, suppose that we now have our frequency is 3/4 omega sub s. That's that pole's location. But this is now j, and remember how we can define omega sub s. Omega sub s is 2 pi over capital T, or we could say that this is now j, and the 2 and the 4 simplify a little bit so that we now have 3 pi over 2t. And we want to know, where does that put us in the z-plane? So now if we map that through our relationship, z is equal to e to the st, then this is now e to the, and now s is j 3 pi over 2t, and that's times t, so that now the t's cancel, and we see we're now at e to the j 3 pi over 2. And where is that? Now if we think in terms of angles, 2 pi over 2 is pi, that's 180. Now we're not quite at 2 pi, we're at 1.5 pi. So this we could think of as being at e to the minus j pi over 2. Or this particular angle we can C as 270 degrees. Well, in terms of the z-plane, if we're on the unit circle, this has a magnitude of 1. That's going to equal this angle, which is minus 90 degrees. And in terms of poles appearing in complex conjugate pairs, we can now say, oh, this now says that we also have z star, which is the conjugate of e to the minus j pi over 2, which is e to the j pi over 2. And this now says that, in fact, we have an angle at 90 degrees, or plus and minus 90 degrees, due to this paired nature of complex conjugate poles. Or, in the z-plane, what we have is, in looking at a frequency that's beyond our Nyquist frequency, here we're saying, let's say that this is now at 3/4 omega sub s, we now are showing in the z-plane that we've not only transitioned around 180, but we've now gone all the way down to 270. But that's the same as going to that point in the other direction, or going in this direction by an angle of 90 degrees. So what we've seen in this discussion is that this frequency is DC, or 0. This frequency, omega, is now equal to omega sub s over 2, which, if we remember what omega sub s is, that's now this 2 pi over cap t, 2, or this is now pi over cap t as a frequency. And what we're showing is that all we can really resolve in terms of analog frequencies are frequencies between 0 and pi over 2, or omega sub s over 2. So that this frequency right here is going to be omega equal to 3/4 omega sub s, but that's now 3/4 of 2 pi over capital T, or that's now 3 pi over 2t, but that now appears as if it is just going to be flipped version of this particular frequency, or that location, which is now halfway between DC and pi over t, or this is now pi over 2t. Or, let me write down what I'm trying to conclude. Therefore, if we had a frequency that was 3/4 omega sub s, which translates, using omega sub s equal to 2 pi over capital T, that translates into 3 pi over 2t. In terms of what we would see in the discrete time signal, that will not appear as a frequency of 3/4 our sampling frequency. It will actually appear as an alias frequency. Let me say omega sub alias, which corresponds to this point right here, but that point has its conjugate value up here, and so we're really going to see 3 pi over 2t as if it is a frequency of pi over 2t. If we had a frequency that was mapped all the way over here, let's say it went all the way around to there, then another way of thinking of it is it would be down by that distance, or now it would look like a frequency between 0 and pi over 2t. Going back up here, then, you can see that all frequencies in the analog setting here we would have, let's say, 3 omega sub s over 2. If we thought about this strip, anything up here we won't really be able to see in that high of a frequency. They will actually be aliased back down into this primary strip. And it will now appear, just like this particular pole at 3/4 omega sub s, it actually now appears as if it's a frequency of this omega sub s over 2. Or I should say this j omega alias, which in our case we had it as pi over 2t. And you can see that it's equally spaced between this point and that location and this point and that location, which is another reason why this particular Nyquist frequency, or omega sub s over 2, is referred to as the folding frequency. Anything beyond that, if we simply fold our paper, then wherever that folded value gets located in this primary strip is what it will appear as an aliased frequency in the sampled waveform. And I hope that now helps explain this connection between the sampling frequency, the Nyquist frequency, which is omega sub s over 2, and this concept known as aliasing.